Welcome. I'm Rick Riss. I'm a senior consultant and market analyst for ARC. We are going to have a session today at 2 o'clock here, decarbonizing electric power generation. And then after we've decarbonized all the electric power, then we're going to decarbonize oil and gas at 4 o'clock. And then all the world's problems are solved. All right? So, so you probably, how many people here have some idea, have their own ideas of how decarbonization and how the electric power is going to unfold? I know you all have ideas. Everybody has an idea. You can't talk to somebody that says, oh, it has to be nuclear. Oh, it's going to be wind and solar. Oh, no, it's going to be carbon capture and storage. Or that's not a problem at all. We're just fine. All right? And so in any event, we all try to keep an open mind and see different technologies. Last year we had speakers from NuScale Nuclear. We like to keep some of the more prominent options available. This year we have three very interesting speakers. We have, we have Mike here from TerraPower. That's the Bill Gates funded nuclear power plant. He's got a little bit different reactor than NuScale. It's quite a bit different than NuScale's, all right? But maybe he's got a better idea, all right? And then we're going to have TJ Conway from Rocky Mountain Institute. He's a special guest here, speaking in both of my sessions, actually. He's quite, Rocky Mountain is very well known in the industry as kind of an industry collaborator to figure out the energy future. And lastly, we have Paul Hibbard. I've met Paul Hibbard as a light commissioner in my town who has spoke at other electric utility activities, and Paul is going to talk more about lots of the rules and regulations and how the utilities are planning for that future. You know, obviously, we have a lot of wind and solar. It's an intermittent resource that didn't escape ISO New England. All right. So let's start out with a short introduction, and then I'm going to get into my speakers. How come forward is moving me here? That's my forward button. Well, I'm just, one more? All right. Somebody's got to get me to my presentation. So last year we had some very good speakers. We also had last year Neil Chatterjee. He was the former FERC commissioner, Federal Energy Regulatory Commission, and we had him speak about some of the regulations that are impacting the future of the electric grid. So, as you've seen, here's our speakers. We don't have any panelists today, but we will certainly have a panel discussion, and we're going to be welcoming your questions. So we have a Slido poll question, and I'm going to give you a hint here if maybe it might influence how you might answer that question. But here in this graph, you can see the history of how the electric power in the US has evolved. And what you see is that coal is the largest source of electric power, has been in pretty sharp decline from about the year 2000 to 2020. And natural gas has climbed, and nuclear has been, had increased for a period of time, but is a little bit flat lately. And then renewables are also growing sharply. And you notice that I happened to pick this one right at 2020. You got all three of those options: nuclear, renewables, and coal, simultaneously almost intersecting. All right. So the question that'll be asked is, by 2030, how will these generation sources rank? And I do break out renewables individually, though, to wind, solar. So there's a Slido question, all right? And if you can scan this QR code, and then you can go and take this slide, and you can decarbonize our electric grid, all right? Or at least predict how the state of our electric grid will be. Maybe you're not going to, maybe it won't be the state to decarbonize. Maybe you're pessimistic and you're thinking it's still going to go back to coal or something, right? But if you take the Slido poll, or if you want to just look it up, if you can't read that QR, you have to remember these digits, the 2111192. And if you take that poll, we're going to come back to this as we move into the panel session, so that it'll just be a very general question to get us started in the discussion. So, we've kind of known about global warming for a long time, and clearly we've been attacking the problem. We've had a Kyoto Protocol, we've had a Paris Protocol, we've had a lot of other government meetings of the minds with commitments on how to decarbonize. But for all of those knowledges, and including the 1985 physicist Carl Sagan, talking to Congress and telling them, yeah, global warming is going to be a problem. You need to work on this. All right. Well, if you're going to work on it, that basically means you have to get CO2 to start coming down. And as we can see, it doesn't look like CO2 has turned the corner yet. This graph has to reduce in slope, go flat, and actually, at least get flat or go down. All right. That's the CO2 in the atmosphere, 420 parts per million today. And so I thought this was a very interesting graph I saw the other day, that here's 1,200 scenarios of how global warming is going to unfold. All right. So they put all the possible scenarios. Some of these global warmings here are up at 5 degrees centigrade. It's like, oh, let's just don't do anything. We're fine. All right. And then a lot of the other ones are, well, we can do various things, but we've pretty much burned, there's 230 paths, presumably out of this 1,200 to actually achieve this 1.5 degrees. But if you look at those 230 paths, most of those are just not going to happen. And most of those actually will depend on actually developing some new technology to take the CO2 out of this room and out of every room and out of the whole atmosphere, which is called direct air capture. Direct air capture is very, very expensive, and obviously capturing CO2 at 420 parts per million is going to be a lot harder than capturing CO2 in a flue gas stack that has very high concentrations of CO2. So presumably carbon capture and storage in those facilities are there. In any event, what it amounts to is it's a hard problem, and we haven't been working hard enough on it. Lawrence Livermore puts these graphs out every year, this energy consumption from the primary sources to the ultimate use. And you can see that we have used a lot of, on the middle side, we can see we have residential, commercial, industrial, and transportation are the main places where all of our energy is going. And on the left side, you can see where all that energy came from. And this is really the raw energy heat of combustion in the case of petroleum, coal, and even nuclear. And what you can see is that a lot of these power sources will be making CO2. On the left-hand side, the ones that are not making CO2 are solar, nuclear, hydro, wind, geothermal, and possibly some biofuels. Biofuels might be considered replenishable. But this was in 2021. If we go back a little bit to, it goes here. No, I'm not pressing the right button. There we go. That was my error. If we go back a little bit just to 2013, all right, what is that, 8 years ago, and you notice the size of the black line for coal, all right? And notice the size of the blue line there for natural gas. And I'm going to go back to the previous one again so you can see the difference, all right? You can see how much thinner that coal line is. So it's clear that we are working on the problem. Coal has been in sharp decline. Natural gas has crushed coal, all right? You would also see that solar and wind have increased in size. Nuclear has been relatively flat over this period, all right? And petroleum for transportation is still about the same. I guess the EVs haven't really made that big a difference. Now you have to ask us, well, everybody has this 2050 date as the date we need to really get to net zero. This is the date we need to have. And on the left-hand side, this is the world's distribution of power generation, all right? And you can see the black slide is coal. And if you look on the right side by 2050, you don't even see coal show up here, but a very thin slice, all right? You can't even see it. And so on the right-hand side, the projection is that the way power will be generated is hugely from wind and solar. It does anticipate a nuclear renaissance because you see nuclear goes from 10.4 to 17, all right? Hydro drops from 15.8 to 7. Now, it dropped from 15.8 to 7 not because hydro decreased. Hydro actually increased over this time period, but it didn't increase the rate at the energy is, because between now and 2050, we will be making 3 times as much electric power, and you're not going to be able to triple the amount of hydropower that's on the grid. You'll be able to increase it, but you won't really be able to trip it.
As Rick said, I'm Mike Donovan. I work for TerraPower. Specifically, I work on the Natrium project. It's a sodium fast reactor. TerraPower is actually working on several reactors right now, but the sodium fast reactor is the one that's closest to completion. We anticipate building one of these in Wyoming no later than 2030. Thank you. There we go. Okay, so as Rick mentioned, we are, one of our founders is Bill Gates. However, we have multiple sources of funding. One of those sources, and a very important source of funding, is comes from our participation in the Advanced Reactor Demonstration Program. This is a program being run by the Department of Energy. They've essentially partnered up with several nuclear technologies to get several plants built in the short term, intermediate term, and longer term. We're one of the short term participants. And the goal is to sort of, get some momentum behind this nuclear construction, this nuclear renaissance, get some plants built, take our lumps in building the first plants, and then ideally, watch the efficiency increase as we get into the N+1 plants. As I mentioned, the Natrium plant is a sodium fast reactor. The coolant, whereas the coolant for most nuclear plants is water, we will be using liquid sodium metal for the primary coolant. And you can see that on the left there. And we will additionally be storing the energy in a molten salt loop, which is shown on the right there. This is pretty significantly different from the existing reactor fleet that's out there, and it gives us some very unique advantages. So why use sodium coolant? Obviously, it's a little more difficult than just using water. I don't want to get too deep into it, but I will say that we use the sodium coolant because in an existing water reactor, and I'm a big fan of existing water reactors, by the way. I worked in them for 20 years. But when you use water for the coolant, in order to make the process efficient, you have to pressurize the water. And when you pressurize the water, it gets, there's more expense in capital expense in building your plant, and it's also just a physical fact that you are working within tens of degrees of safety margin, which has historically not been a problem. But one of the advantages of working with a sodium coolant is that we will not have to pressurize the sodium in any way. It can essentially be at atmospheric pressure, and we'll be operating hundreds of degrees away from the boiling point of sodium, which really makes for a more robust safety case for the newer reactors. Here's an overall picture, cross-section, obviously, of the reactor. I'm not sure if anyone's familiar at all with existing water reactors. You'll notice a stark simplicity here. It's a very, very simple overall design. Passive cooling such that walk away safe. We don't require any safety-related power, so it's inherently safe design. Very efficient with the sodium cooling. So I will also say, in addition to the advanced physical design of the plant, we're also taking advantage of some new codes and standards that are allowed by the Nuclear Regulatory Commission that allow us to build the safety case not so much on old-style deterministic safety case, but more of a risk-informed or probabilistic safety case, which allows us to really address the true risks and not unnecessarily spend a bunch of time and money on wasted effort on things that are not truly risks. So this is another positive step forward for advanced reactors moving forward. I'll also mention sodium fast reactors. We're moving this technology forward, but we're not the first ones to build one. These have been built in the US before, slightly different variants. Fast flux test facility, EBR 1 and 2. So this is an evolutionary next step of this technology. One of the primary features or strategies that we're undertaking here for Natrium is that we're going to focus the nuclear island, which is more circled in orange there. That's where the nuclear reaction is going to take place. That's the part that's subject to regulation by the NRC. We're making every effort to keep that completely separated out, both physically and functionally, from what we call the energy island. The energy island is the part that's in blue up there. And in this way, we can maximize sort of commercial standards and lesser regulatory restrictions on a large portion of the plant and really have the NRC focus on the portion that is safety significant. Existing plants today essentially are all built together without significant separation. Let's see here. And so another thing that utilities are looking at nowadays, obviously, nuclear plants historically have been capable of load following, but it's not been their strong suit. So we've got these nuclear plants that provide really good, stable base load, but they like to run at the same power level all the time. Meanwhile, on the grid, we've got significant penetrations from renewable. We've got solar that's putting out a lot of good, cheap, reliable power during the day, but not so much at night. And similarly, with when the wind is blowing, you get a lot of wind turbines spinning, but not all the time. So how do we level all this out? The Natrium works on this by integrating not only the nuclear reactor, but also thermal energy storage. That is a technology that's become well developed in the solar industry. And so a Natrium plant consists not only of the nuclear reactor, but the nuclear reactor dumps its heat into this essentially thermal battery storage or molten salt energy storage. And the output of that energy storage can fluctuate with grid demands. Additionally, it works really well hand in glove with renewables, because an operator, a utility, will have lots of renewables, and the operator needs some way to levelize the load. So the idea here is that through the energy storage system that's part of the Natrium, they will also be able to integrate solar and other forms of energy, and essentially when the grid needs power, use the salt to generate the power. When not, you just build up the level of the salt until you need the power. This is just a quick cross-section. On the left, you can see typically what's the safety-related portions of a light water reactor. You have lots of safety-related pipes. If you have certain event that takes place, the plan to maintain safe shutdown involves a lot of active pumps, pumping water into pipes and so forth. It's worked well. It's a very safe system. It has a great history. On the right, though, you'll see the step change in simplicity. For the Natrium reactor, essentially gravity drops the rods to the bottom, air circulates to discharge the decay heat. You don't need any active cooling whatsoever. Here you'll see we're taking advantage as well of new excavation techniques and building techniques. On the right there, the small square is essentially a bored hole down in the ground. We have our eyes on building multiple of these Natrium plants, and the idea is that we'd be able to go in there, drill the hole in the ground, drop factory assembled components down in it, in the span of 2 to 3 years, have a plant up and running. On the left there is a ESBWR, and I'm again a big fan of the boiling water reactors as well. But you can see there the overall size of the excavation, the time needed for construction, the regulatory engagement associated with that instruction. We're attempting to minimize that the amount of that. Also, another advantage to the sodium coolant, the radionuclides generated within a nuclear reactor have a great affinity for the sodium coolant, and it has the effect of trapping all of that radioactivity in. we'll be able to, a typical pressurized water reactor in the U.S. will have an emergency planning zone going out 10 to 20 miles. We anticipate right now the emergency planning zone for the Natrium reactor to essentially be at the fence line of the facility. So the key differentiators with the sodium fast reactor, particularly with Natrium, we intend to focus on the nuclear island and keep it separate from the energy island. That minimizes costs and oversight, speeds. It allows for parallel development of those two things to make construction quicker. We are working on advanced fuel that makes the SFRs even more cost effective than they were previously, and the integrated energy storage. Here's a sort of an instructive cross-section. Again, I am a big fan of the existing fleet of reactors, but on the top there you'll see a cross-section of an AP1000. You can see the complex interrelation of all the pumps and cables and pipes, similar for all of the existing or previous reactors. And then you can see the Natrium by comparison there. It's really just a single pool of sodium at atmospheric pressure generating heat that then gets used. There's not this complex spider web of safety-related pumps and motors that require power. It's not passive. We're also doing a lot of work on fuel. I won't get into this too deeply, but I will say that nuclear reactors generally work either in the thermal range of the fission neutrons or in the fast range of the fission neutrons. And essentially all of the reactors out there now in the U.S. work in the thermal range, which is great for generating power. It's worked great. We'll be working in the fast spectrum, which gives us several advantages. One, it allows us to generate much more heat. We can heat the sodium up to 500-600 C, which makes the energy cycle much more efficient. It works much better with the energy storage. It also allows a much more efficient and complete burnup of the fuel. So it has several advantages. Again, another look at the thermal energy storage. This will serve not only to capture all of the energy coming out of the nuclear reactor, but also each utility will size these appropriately to levelize load with all of their other energy sources, including solar. And so right now, we are working on the Natrium demonstration plant. That's a great effort to build this, sort of first-of-a-kind construction effort. We do anticipate to learn a lot in that process, and then we have plans for subsequent iterations that will be significantly even more efficient to construct and run. And ultimately, going on out there a ways, the sodium fast reactor gives us the opportunity to, in the future, do things like potentially burn up. There's a lot of energy still left in what's termed spent fuel right now with the existing reactors. Fast reactors, theoretically, and in the lab, will allow us to, reuse or extract the remainder of that energy out of what's considered used fuel that's being stored out there right now. It's not without its own challenges, but operating in the fast spectrum will allow us to focus on that and work towards that out in the 2040s. Also, I just want to acknowledge, I'm not sure who all may be out there, but TerraPower is really standing on the shoulders of giants. We're working cooperatively with quite a number of industry partners, including utilities and manufacturers, even one might consider competitors. And so this is just a quick snippet of some of the folks that we're working with. And that's my quick introduction. I'm very glad to get with folks. We'll have a Q&A after the presentations, and also I'm glad to discuss it in more depth with any of you after the meeting today. So thanks again.
All right, well, thank you very much. Thanks, everybody, for giving me the opportunity to speak here on behalf of RMI. As we said earlier, I'm TJ Conway, Principal in the Climate Intelligence Program at RMI. I'm going to be speaking today about at least in this panel, about virtual power plants. And this is actually part of our carbon-free electricity team's work. I will do my best to be a good messenger, but if I can't answer your tough questions, I will be sure to get answers later on from my colleagues. For brief background on RMI, RMI's mission is to transform the global energy system through market-driven solutions that align with a 1.5 degree future for the secure, a clean, prosperous, and zero carbon future for all. So, not ambitious by any means, but we are, that's kind of where we're standing. Kind of, you'll kind of see, maybe some of the priorities we kind of set out based on that mission that we have. So let's jump into virtual power plants. I will talk first about and I'm going backwards and forwards, just what are virtual power plants and how we define virtual power plants. What are some of their benefits? And I'll elaborate further on some of the partnership ideas that we're putting forth here through the Virtual Power Plant Partnership, which is quite an interesting and recently announced partnership. So the timing is actually very good. Let's jump into it. So what is a virtual power plant? At a high level, a virtual power plant is an aggregation of hundreds or thousands of grid interactive distributed energy resources. Okay, so what does that mean? We can break it down into kind of three component parts. The first is what we would call what we call here the tech, but that's really the distributed energy resources. You can kind of see in the graphical depiction on the right, it's the combination of all the devices that you can see colored sort of under the distribution there. They can come from residences, they can come from businesses, they can come from the transport sector, but collectively these various devices can provide some support to the grid, and they can also be, many of them can be readily dispatchable. If we're thinking about behind the meter batteries, for example, some of them might not be as dispatchable, but they can still be used in aggregation, and so that gets to the second key aspect, which is aggregation. This can take various forms, but generally speaking, there is some form of an aggregator, virtual power plant aggregator, that is helping to kind of bring all of these different devices together and can leverage that to bring power onto the grid, or to also match sort of supply and demand at any particular point in time. And then there's grid integration. And grid integration also implies, VPPs providing value to and interacting with the grid and markets. So the value is an important component of this, in the sense that if you are, if the ISO is just saying, please cut back your consumption right now, and everybody tries to comply in order to avoid, more catastrophic consequences, that isn't a virtual power plant, right? Because there is lost value there. The idea is that this grid integration allows this opportunity to emerge. So that is our definition. I would say that some might suggest that this is quite a broad definition. I think that's fair, but we do want to take kind of a broad approach in thinking about this as a concept. There are a lot of applications and a lot of potential benefits. So let's maybe jump into some of those benefits and potential. You can break it down into maybe 5 different buckets, 6, I guess. The first is reliability, right? We know sort of that there are reliability challenges. That's a very important sort of issue and consideration these days. Our estimates are that by 2030, virtual power plants can bring on sort of 62 gigawatts of peak coincident dispatchable capacity. And that can rise all the way to 200 gigawatts by 2050. Now, peak coincident dispatchable, that's a lot of words at once, but what it really is meaning that at peak capacity that can be dispatched and all at the same time, right? So that might mean that there are a lot of different sources and devices, but at any one point in time, there can be 62 gigawatts brought on. Some have said that even this number might be quite low, that there's actually much greater potential, but those are sort of our estimates. Second is affordability, and this is, I think, primarily through the fact that this can help to limit the amount of additional power sector expenditure through new generation units that have to get brought online, right? So it's sort of more efficiently leveraging what we currently have or what is coming on through DERs or distributed energy resources. And that helps to kind of reduce the overall cost. There are also health and equity benefits. So, if this can help support the reduction in consumption of fossil fuel-based generating sources, that can have benefits for fence line communities and the population at large as well. And fence line communities too also tend to be those that are sort of lower income, more marginalized in other ways, so it has additional sort of equity benefits, not just health. The final two are kind of the most obvious, perhaps, but kind of unpacking what we really mean by decarbonization is quite interesting because, as I said, you can reduce the amount of new fossil fuel generating capacity coming online. You can also just decrease the use of fossil fuels at any particular point in time. So especially during, in peak events, for example. This also is very compatible with build out of renewables too, so that complementarity supports the build out of renewables. And then finally, there is sort of this electrification component. And this also is it's important to think about in the context of the transport sector, right? Where we're starting to see electric vehicles take off, and as we saw, maybe they're not moving the needle so much in terms of the role that they're playing in helping to curb oil demand, but there's a lot. If you look out over the rest of this decade, I think there's a lot of evidence to suggest that we are at or nearing an inflection point in terms of the adoption of electric vehicles, and having this ability to better leverage what are effectively a bunch of batteries is very important to help grow electrification and to do so in an effective and cost-efficient way. So just a little bit more background on how VPPs work. So I'll lay out kind of two different models, but there's actually 57 different flavors. And the first though is a market participant model, right? And this is where you have a wholesale market operator, ISO, RTO, where they're sending a price signal for additional capacity, ancillary services, et cetera. And they send that signal to an aggregator. That aggregator then works with the various members of that aggregation, and they bring more onto the grid. They provide more onto the grid, in response to that, or also can reduce their consumption at any particular point in time to help with balancing. In response, the RTO or ISO will compensate the VPP aggregator that in turn provides a financial benefit to their members. And what's interesting is that this is not just theoretical. We actually have plenty of cases of this occurring today. And what I'll talk about a little bit later is that the biggest issue is really trying to scale this solution, not prove the concept up. And so, if we're thinking about the specific case of market participant VPPs, we actually had an important event in a very significant heat wave in California in late August, early September, and we had exactly this occur where California's ISO sought support from a bunch of different aggregators. One being Connect, which has 200,000 different members and 250,000 different dispatchable devices. They were able to, to support them alongside others like Tesla and Sunrun. The power or the sort of fluctuations in demand needed in order to help that balance out to some extent, and that Connect in turn was able to generate value and pay about $2.7 million back to those that were part of that aggregation. So this is being borne out in reality. The second example is what we would call a retail VPP. So this, doesn't really have, this is more of an interaction between the utility and customers. So it could work sort of in a deregulated market context. It could also work in a regulated market context. But the nature of the relationship is really between the utility and they are sort of key to aggregating these different utility customers. And the payment approach might be slightly different, but the idea would be to have certain types of programs that utility customers can sign into and provide annual payments for which the utility can then ask VPP customers to or the utility customers to again adjust supply and demand as needed. And this, again, getting to the point of this being a relatively simplified model, you can also have third parties involved here. It doesn't have to be direct relationship between a utility and the customers. It can be more complex than this. But we do have, again, examples of, for example, National Grid's connected solutions being an example of a retail VPP, and that actually has helped especially in sort of peak summer demand circumstances. In 2020, for example, we saw peak summer demand, VPPs helping to reduce peak summer demand by about 1%. So that's material impact. So that is kind of where, so we've got the proof of concept, and I think, RMI, we don't like to call ourselves a think tank, we like to call ourselves a think, do, and scale tank. And when you get the doing is kind of the proving the concept, and then the scaling is trying to scale that concept. And that's where the virtual power plant partnership is coming into play. So we've just announced this in the last couple of weeks, and we have a range of founding members. You can see here, it's automotives, it's tech, various tech players, and various actors that might have some interest in sort of virtual power plants really taking off and scaling. But this is not, I'll talk about sort of the wider ecosystem toward the end. But these are our founding members at the point of me delivering this presentation. They're delivering this presentation to Rick about a week ago. But the founding members, I can say there might be more coming in the future, and there's definitely quite a lot of interest here. But the mission is to, as you can see here, to catalyze the industry and really change the necessary policies, regulations, and market rules for VPPs to take off and kind of yield the full benefits that we expect there can be. So we have sort of addressed and kind of thought through what some of these barriers really are, and that will be sort of the emphasis of the work that we will seek to do as part of this partnership. The first is just around sort of some of the wholesale electricity market rules. So we have there's policy, there's technology that I mentioned before, and policies kind of coinciding with technology to make this more and more of an interesting opportunity. And that is the key policy is FERC Order 2222, which requires ISOs and RTOs to allow distributed energy resources to participate in wholesale markets through aggregation. But really putting this into practice is quite complex, and so it gets very thorny very quickly. There are a lot of different challenges, whether it's for, just in terms of the timing of the implementation, what is the scope and the eligibility of the different types of aggregations, metering requirements, and sort of the data access, the list goes on. So helping to kind of understand and work through some of those challenges is a first priority. The second is, and maybe it kind of lines up more with the retail VPP model, is the retail utility programs and offerings. So for various reasons, the retail programs may not be attractive or not even available in certain cases yet. And the reasons include everything from just how reliable people perceive VPPs to be, regardless of the reality, the lack of infrastructure like smart meters and software, lack of integration of different types of programs that utilities have. Right, a utility might support 3 different types of technologies, but not necessarily in an integrated way. And that could be for regulatory reasons, not just because of the utility's choice. So, and then finally, sort of the inherent financial incentives around rate basing and legacy planning, et cetera. And then finally, there's industry and policymaker awareness of VPPs. And it's not simply just letting people know that they exist, but rather, if you think about it from the provider's standpoint, there's a significant cost in trying to communicate and explain how all of this works, and sometimes that cost is just prohibitive. So helping to kind of educate the public around what VPPs are and what they can be is also a critical challenge. And so those line up relatively well with some of the priorities that that VP3 is focused on, right? Trying to better communicate and research the benefits, develop best practices across the industry, and then help inform and shape policy development. I don't want to go into the details, but we've got sort of plans to work with the range of different partners and stakeholders over the course of this year and beyond. I'll kind of land on this slide that we're not just thinking about the partners within VP3, but also the wider ecosystem, and how we seek to kind of work together with various groups, those advisors and collaborators, and also provide some of this information on the benefits, et cetera, to various target audience at the state and federal or regional levels. So we are not trying to do this in a vacuum. We understand that this is a diverse ecosystem, and seek to kind of leverage all of that to further develop the concept of virtual power plants. So I'll leave it there, and thank you for giving me the chance to speak.
Thank you, Rick. And we've just had 2 incredible presentations of decarbonization technologies and processes that are going to become extremely important in the decades that come. And as I was listening to them, I was thinking a lot of what I'm going to do is bring it up to a different level, talk about why the whole process of decarbonization looks so almost impossible and difficult in general, but why it's important. And secondarily, focusing in on the electric power sector, just some of the immediate issues that are apparent where states are taking action to decarbonize their energy systems, and where technologies like the ones that TJ and Mike discussed could become incredibly important elements of the whole process of decarbonization for the electric power system. So let's see if I got this right. This one? No, this one. So just as an overview, I'll talk a little bit about why decarbonization is necessary and why it's so incredibly difficult. It's easy to hear presentations about the various technologies that are in development that can help us decarbonize, but then when you step back, and a lot of what I'll do is kind of playing off of some of the slides Rick put up, when you step back and take a look at where we are and what remains to be done, it can look a little bit daunting. And so I'll talk a little bit about how we're doing and what some of the emerging policy approaches are for decarbonization and the associated technologies with that, and then what some of the unique challenges are in the electric sector. That's back. So why is this so difficult? And I think this is probably obvious to everyone, but it's difficult for 3 very simple reasons. Human well-being is incredibly dependent on energy. If you think about almost everything you do on a daily basis, it's intractably tethered to using energy, from population growth, wealth, industry, commerce, nation building, healthcare, technological advancements, buildings, transportation, everything involves or is dependent on the consumption of energy. And you'd be hard pressed to think about your day-to-day and find an example where energy wasn't necessary for what's been going on. And the second piece of this puzzle is that energy is essentially synonymous with fossil fuels. It always has been, and it still is almost everywhere. And I'll talk a little bit about that. And then the final piece is, of course, fossil fuels is synonymous with climate change, potentially catastrophic social and economic circumstances in a relatively short time period for civilization if we don't do something urgently about it, do something very soon to address it. So, as Rick mentioned, really what is expected from the scientific community, the consensus is that we have to stay in the range of 1.5 to 2 degrees Celsius, and some say it's even potentially lower than that, to avoid these catastrophic social and economic impacts of climate change, and to reduce the risk that we pass certain thresholds where we have runaway circumstances that are even faster than what's expected in a base case analysis of the impacts of climate change. And doing this requires, as Rick mentioned, achieving net zero CO2 emissions across all sectors by mid-century on a global basis. And it's really, if you think about it, it's nothing less than eliminating the use of the only concentrated economic source of energy humans have ever known in 30 years. Meaning gone in your lifetimes are coal, oil, and natural gas, burning any of those. Gasoline, diesel in the cars and trucks that burn it, jet fuel in the planes that use that. Most power plants in current operation, and all of the stoves, water heaters, boilers, furnaces, and everything in any home or business that currently uses oil, propane, natural gas, or wood. And of course, the heavy industry use of hydrocarbons. All of this gone in 30 years. It's almost inconceivable to think about it. And when you start looking at the technologies that are available right now to do it, we very quickly go from some of the low-cost alternatives to things that are very expensive to decarbonize, which just kind of sets up a circumstance where you have the kind of innovation that Mike and TJ were talking about, and a lot of investment right now going into bringing down the cost of technologies and finding new technologies to help us achieve that. So some of the expected abatement options include, some of them are really well known and they're existing technologies and they're already something can be taken advantage of, including energy efficiency and coal to gas fuel switching, onshore wind and solar, hydro, nuclear, existing nuclear. All of these are mature technologies that can help us decarbonize and that are relatively economic. But then that will only get us so far, and in fact, not very far. That's when we need to start moving into things that are in progress, are in process in terms of research and development, but that currently do not necessarily look like they're very economic, including vehicle electrification and building electrification are coming close for a lot of people, but still wouldn't say that they're economic enough to be adopted in a widespread way in the next 10 years anyway. But battery storage, alternative fuels for industry and for transportation, renewable natural gas and hydrogen, the advanced nuclear technologies like Mike was discussing, and then ultimately carbon capture and storage, and Rick mentioned this a little. I mean, what would really, really help us is if some of these direct air CO2 capture technologies became economic in a short period of time. A lot of the challenges associated with decarbonization would go away quickly, but that doesn't seem likely at this point, at least. And so how are we doing on the path to decarbonization? You'll see this when you watch the Super Bowl next weekend. You can see it in ads and TV now and in popular magazines. It seems like we're doing great. We have Shell suggesting that what's important here is our children and our grandchildren, and maybe we're going to be charging our phones with our shoes. And Shell is obviously very interested in solar and sees a bright future for that. I mean, all of the oil majors. BP apparently is investing a lot in solar, according to this ad, and Chevron thinks it's time that oil companies get behind renewable energy. So it seems like we're doing really well. But of course, we're not doing well at all yet, and the chart on the right here shows it. We are still on a global direct primary energy basis, almost completely dependent on fossil fuels. Every color that you see there, the writing's kind of low, small, I mean, is a fossil fuel. It's biomass, coal, oil, and natural gas. That gets you all the way to the top where it looks a little bit purple, and just that little teeny wedge at the top is the emergence of zero carbon fuels on a global primary energy basis, not just the electric sector. So it feels like a lot's going on, But when you take a step back and look at where we are, it still seems like we have a very, very long way to go. The share of primary energy from fossil fuels, this is just looking at 2019, almost every country is somewhere between 75 to 100% dependent on fossil fuels for their primary energy. There's a handful of countries you see on here, Canada, Brazil, the Scandinavian countries, where they have an immense amount of hydro and some other renewable resources that are the exception, but every other country here falls in the bucket of 75 to 100% dependent. And the pie chart on the bottom shows that where coal, oil, and natural gas dominate our primary energy consumption on a global basis. And it's not really different if you're looking at the US or if you're even looking at states that have extremely active climate policies and regulations that are beginning to take hold. The top chart it's a different version of something Rick put up there. This is our primary energy production in the US, and you can see the good news is that blue line dropping steeply, dropping by about a half from about 2 quads to 1 quad over just the last 10 years, and that's coal. But you can see that that's been more than offset by the increase in our dependence on gas and oil, which are the brown and green ones that you can see increasing on the top as a share of our primary energy production. And of course, on here is the steady operation of nuclear and the increase in renewables. But again, it's been, even over the past 10 years, we haven't been making progress because of as Rick pointed to, there's an increase in consumption associated with an increase in demand, so that the renewable gains are being offset by an increase in consumption of fossil fuels. And it's true at the US, it's also true in New England and Massachusetts, where there are very active climate policies in place. Things are certainly happening, but it hasn't made a big difference yet. What really has seemed to have changed over the past 10 years is that all of the states that for decades have had goals and targets around reducing greenhouse gases have, over the past 10 years, all of those goals and targets have become or are becoming requirements in legislation. They're actual legal requirements. In some administrations, the EPA has taken efforts to incorporate climate change in its obligations under the Clean Air Act, but certainly in specific state laws, increasing number of states are passing very aggressive climate policies. And then they're now not only focused on the electric sector. In all of these cases, the climate policies are focused economy-wide. And they're on a schedule focused that are consistent with the scientific consensus to get to net zero CO2 emissions by 2050. The state laws that are on the books now, you can see that all of them incorporate very specific requirements to get to somewhere between 80 and 100% reduction by 2050. And the states are pursuing pathways to achieve that. The interesting part in the US, I mean, there's always a question about, well, a handful of states can't really accomplish too much. But even if you just look at the states with active climate policies on the books now in legislation, it amounts to well over half of the United States economy, even though it's a minority in terms of the number of states. So the key policy and technology challenges that will need to be addressed is, as I was mentioning before, everything and the cost of everything is affected by climate policy. And the transformation of the energy economy is inevitably going to lead to large transfers of wealth among companies, across geographies, across socioeconomic strata. And there will be many winners and losers, which is good for a lot of companies and a lot of people, and bad for others. There is a risk of hugely disproportionate impacts on low and middle income people in the population. A reason why you see so many of the state policies and even federal agency policy development focused on equity as part of the energy transformation. But there really is, even given those, remaining a very significant risk of disproportionate impacts. And there's even though we have these emerging technologies like TJ and Mike were discussing, there still remains, I think, a really high degree of uncertainty around the feasibility and the cost associated with the fuels and technologies that will be needed once we manage to capture the low-hanging decarbonization fruit. And so The way it looks now and the way states are rolling out policies now, I would say the preordained pathway to decarbonization involves intense electrification of the transportation and building sector, including organized build-out of vehicle charging, both roadside and at home, and direct subsidies for EV purchases, combined with, in the building sector, rolling out specific subsidies and incentives for the installation of heat pumps, both in some cases making it a requirement in new buildings, but also pushing for a more rapid evolution of that technology being used to replace traditional fossil fuel-based furnaces and boilers. I apologize, I'm starting to lose my voice here. And then combined with that, simultaneous rapid decarbonization of the electric sector. So one thing I'll just focus on in a couple of slides here is just looking at that electric sector problem and how this focus of decarbonization policies creates some challenges in the electric sector. Challenges that, ironically, are things that the technologies that TJ and Mike were discussing could be incredibly helpful for solving it. So I'm just going to skip through this one. This is just showing the impact on a small municipal utility of what this level of electrification that's currently being required in some state climate policies could have on, just imagine a small electric municipal, but it will be true for all the investor-owned utilities as well as municipal utilities. The light blue on the bottom here is the electricity demand profile, 8760, for the utility right now. And then the red involves how that would change with increased electrification of the vehicles within the utility service territory. And then the green is in the different shades of red, the red and the pink. One is sort of commercial industrial transportation. The other one is residential. And then the green is the same thing for building electrification. And you can see that it not only completely changes the load profile for the utility, it actually shifts the utility's peak demand to the winter from the summer in this case, and massively increases the variability in following demand. So the implication here for each utility is there's going to be needed a huge amount, absent the emergence of technologies that can do it for them, a huge amount of investment in distribution system infrastructure. Similarly, if you look at the RTO level, I imagine this is very hard for you to see out in the audience, but what I want to focus you on is this is looking at New England and New York multi-day periods. Imagine you're looking at electrification demand associated with a significant amount of electric vehicle and building electrification, but also where the states and the regions have developed and have operating the amount of solar and wind and even battery storage that currently are being pushed through state policies, through the state policies in New England and through the policies in New York. So what does running an electric grid look like under those conditions? And so the profiles for generation from solar and wind here are essentially following expectations of output based upon historical operation and electricity and solar profiles. And then you put in the baseline the operation of the existing and continuously operating nuclear and hydro facilities in there. And you can see what the profile looks like taking out fossil fuels altogether. And so what I want to focus you on are the periods here. In the blue on the left, it's like a 4 or 5 day period of where there's suppressed wind generation and, of course, no solar at night. And then over on the right in the gray. And it just kind of quantifies that even with massive amounts of solar and wind being added to the system, there's something needs to fill that gap. And whether it's Mike's modular nuclear reactors that are using the storage capability to manage this variability, or if it's 30 or 40 gigawatts of distributed resources that are aggregated and because of FERC 2222 are able to participate in wholesale markets, or maybe it's just batteries. But something has to fill these gaps in order for us to decarbonize over the next couple of decades with electrification and with the retirement of the fossil generation that currently provides that reliability support in these regions. It's a challenge that I can tell you the RTOs are thinking about 24 hours a day, 7 days a week, and it's giving them a lot of heartburn. And this is just another example of this. In New England, if you look at the far right chart here, it's showing the impact of adding in the variable generation onto system operations and the ramping requirements needed to reliably run the system. And so right now on the far right here, this is just a peak day in January that involves about half of the vehicles and half of the buildings having electrified, but also it includes all of the state-sponsored renewable generation in operation. And there are days where the system needs to ramp by 13,000 megawatts, and that's about half of the peak summer demand in New England. There'll have to be a ramp of 13,000 megawatts on the system across the order of a couple of hours. So it's not only a huge resource and resource planning issue for the regions and the states to keep the lights on, but it's also a huge operational challenge for the RTOs as more and more of these variable resources come online. I mean, right now, the role is filled by peaking resources that burn oil and natural gas. But in the future, we have to figure out what the technology that's used for decarbonization has to be able to manage these operational challenges. I'm going to skip this slide. It's really just showing how different scenarios for the demand for natural gas going out as the system decarbonizes. And the thing to take from this is the black line at the top is really the total, it's a supply curve for natural gas in New England. And then as we decarbonize, the line keeps changing and the area under the curve gets less and less. So we are certainly decarbonizing. But what you notice is that the peak demand for natural gas in the winter really doesn't reduce that much. So there's until some other technologies emerge, we're going to continue to need for decades all of the gas-fired capacity that's on the system in New England and New York to manage fewer and fewer hours and lower need for natural gas. But all the capacity will be needed there to keep the lights on for several days a year at least. Anyway, so I'll just wrap up with this. The thing about environmental regulation historically for the criteria pollutants is it's always been a continuous evolution of technology development and then technology forcing standards and then more development. We are not well prepared with our history of environmental regulation for managing the pace and scope of what will need to happen over the next couple of decades to achieve these decarbonization goals. The rapid growth and rapidly declining cost in the technologies that Mike and TJ have talked about and many other technologies is absolutely essential for getting to net zero by mid-century. And the sheer magnitude of the cost across all energy uses will require really close attention to the impact of this transition on low and moderate income people in the country. And just the final point that I was touching on there is that we can't wait 10 years to figure out how we can manage electric power generation and electric power system operations as this decarbonization happens. We need to really be thinking about, and a lot of people are, of course, thinking about how we manage these kind of operational challenges now, if in 10 years we're going to have added all these variable renewable resources at the same time that we're increasing and changing the shape of demand through electrification. Certainly in the short term, natural gas will play a vital role, but the real question is what will be the economic technology that helps us deal with that in the later years. So again, sorry I'm sounding so squeaky, but thank you so much for listening, and I look forward to the questions.
So let's move on to our Slido poll. Let me see if I can get that one up here. That's that little Slido thing right in the bottom. Do I have to just press forward? Yeah, there we go. So we set up the Slido poll. Well, let's see how our audience is. The purpose of this is really just to kind of get a discussion, Which oil and gas sector has the best? No. This is the wrong Slido poll. All right, let's just move over and bring up the, that was the Slido poll for the next session. All right. We can fix that in the next session, but we can't fix it here. But maybe we should get a few comments on the show of hands of all of the energy resources. Let's move this one off. And we were kind of showing that coal was on decline, natural gas was going up. Who would seem to think that natural gas is likely to be our biggest source of power by 2030? I think a lot of us are thinking that. You know, obviously, solar and wind were both growing. You know, I think wind was growing pretty fast at first, and solar has more recently made a lot of gains. Will solar and wind collectively were just rising at the same time coal was declining. So we have every expectation that the sum of solar and wind would be exceeding coal. Does that sound reasonable? By 2030. So coal will still decline. Obviously, there's a large amount of coal still being burned throughout our US, and a lot of that will be moving to natural gas perhaps. And in New England, we have moved most of our coal off of our grid, and our next problem, as Paul was showing, is how do we get natural gas? What's going to happen, and how do we replace natural gas? So let me think a couple of questions for our panelists. So Paul, you were showing us some of the distinct problems, and I know that you have consulted with the ISOs and the RTOs. Why couldn't, and you also demonstrated that there's all these state initiatives. You know, we have the Regional Greenhouse Gas Initiative we have the Massachusetts S.95. We have all these state regulations that are telling utilities do this, utilities do that, and you're going to decarbonize this. Well, why didn't we just have FERC do all this? Shouldn't this be a federal function? Why is every state making their own rules and guidelines?
I think there's a relatively simple answer to that, and it's because the feds have not done it. There's I've often said there's a really, really simple way to do this, which is just put the right price on carbon across all sectors of the economy at the federal level and walk away. We don't need to be sponsoring winners and losers in the resource race. But obviously, that's very politically challenging. So it's left to either the feds or the states to be looking at the data and deciding what looks like the most economic way to achieve decarbonization. Since it's not happening at the federal level, I think a lot of the states, the forward-looking states with respect to climate, have said we can't really wait, that the issue's too urgent and it's potentially too damaging to populations, and they've just gone ahead with their state regulations. And as I mentioned, I think the collective thought amongst the states that are taking action is that it's not happening at the federal level. If enough states do it, we can essentially create the economic and industry conditions for decarbonization without federal action. And it's true that, the vast majority of the US economy is actually, in terms of gross national product, is in the states that are active with climate laws. So, the impact of action by the states that have been very active is real. It actually amounts to, I think, even if you just look at the RGGI program, which is one small piece of what the states are doing, if you put together those states that make up RGGI, it would be the 5th largest country in the world. And so I think those states don't really feel the need for federal action. They don't need for FERC to do it or EPA to do it. They just feel that by collective action of enough states, you just create those economic and industry conditions for our economy to shift to a decarbonized economy.
Yeah, so if I'm part of these RGGI states and we're doing our fair share, what about those other guys that aren't? Of course, we love to blame China, on all of the CO2 emissions they have. But at the same time, you see China is the massive developer of wind and solar.
Yeah, I think on the one hand, you can look at that and consider it a cause for inaction. But I think the states that have acted have gotten to the point where it's like, we can't not do something. They've come to the political conclusion that we understand the risks associated with climate change, and we need to reach net zero by 2050. And the fact that other states or countries are not doing it is just not a good enough reason to not start taking action on their own.
I can
All right, we have some questions from the audience. I see Peter back there.
I'll fit it in.
Yeah.
Hi, Peter Manos with ARC Advisory Group. TJ, my question's for you. We have in common that our original college degree was philosophy.
Okay.
I then went into engineering. Yours was economics. And my question for you is philosophical economical.
Okay.
I loved your mention of the 23 billion to 73 billion of external health costs, externalities, health costs associated with the reduction in natural gas fired generation that could be achieved with demand response. When I look at the annual EIA data on demand response and energy efficiency, it looks like it could be multiplied by 10 and still not be coming anywhere near saturating the market. It's much smaller than we would like it to be.
Yeah.
And my question is not about how those numbers are derived, but about externalities in a wider sense. How do we get the general public and decision makers and then policymakers to really touch and feel like the potential benefits that greater participation in virtual power plants with demand response could achieve? And I'm going to give you a very silly example. A couple weeks ago, my daughter moved out of the house for good. My wife said, "Hey, IKEA has a deal. If you return furniture fully assembled, we can get up to $250 for our daughter's desk." And I'm like, "Okay, honey." And I'm like, "Oh man, it won't even fit through the door. I have to disassemble it, bring it to IKEA, reassemble it." And when I ended up reassembling it, that particle board starts falling apart. I only got like $100 for the damn thing. I made less than $20 an hour for that effort.
Right.
Right? It's not like the engineer ROI, but you know what? I felt good at the end of that endeavor because I said to myself, that thing's not ending up in a landfill. Someone's going to buy it. So we get so into what's the ROI? Can we really get people incented financially to do this when they might be willing to pay a premium or go to some extra efforts
Yeah.
that we haven't marketed very well, if that makes sense?
No, it's great. It's really important. I mean, I do think that you can also think about this, that there will be willingness, even in that circumstance. I think trying to ascribe some type of value to that is important, simply because there will be plenty of people who will say, "No way." I think that we can also kind of think about this more broadly. Some of the most fascinating work is around behavioral economics, right? And with O-Power, for example, we saw that just telling you what other people nearby you consumed is enough to get people to limit their consumption at any particular point in time. So I think that it is good to kind of think about sort of the broad incentives and not necessarily think about this solely around price. But I think that at the end of the day, especially to kind of justify this in the context of this versus new generating capacity, you do kind of need to have a sense of like, okay, what would the savings or the cost be for virtual power plants? So great question. And the final thing I'll say is on externalities. I'm going to talk about that a lot in the next panel. So yeah.
Questions up front here.
Yeah, this is more or less directed to DJ also. The thing I would want to bring up is how are you going to deal with the challenge of you've got this huge disparity of utilities across in states and municipalities and locals with all a complete range of different rules, regulations, et cetera. I know you brought that up as a challenge, but how are you really going to deal with that? Because I mean, I've had to contend with this personally. I mean, I have my own solar array. It goes back in the grid. So one utility decides to spin off another one. They come in and they just arbitrarily change all the rules. One used to pay me for my power. Now the other one decides not to. They don't seem to be constrained really by state, local, municipality, or local laws or regulations. They just seem to arbitrarily do what they want to do when they want to do it. So, I mean, that seems to be the reality that's really out there. So how are you dealing with that challenge? Because a lot of this power is going to have to be generated at almost at a residential level, if you will.
Yeah, I mean, this is probably just there's probably a broader question around just how to incorporate DERs in general, not even sort of with a virtual power plant type business model, and I think the reality is that we've been kind of grappling with this since the order was put out in 2020. But I think that, as we look forward, it is important to acknowledge that this can yield a lot of benefits, and then find ways, incrementally in certain circumstances where it might be really tough, but also try to accelerate and scale where we are seeing success. So not pretending that this is going to be easy, but also just highlighting that there is a huge opportunity here, and it can actually generate pretty widespread benefits. So yeah, take your point completely.
Good. Do you have a question for Mike?
I have a question for Paul.
All right. It includes Mike? I got a question for Mike first, because I don't want to let him get out of this conversation, and then we'll come back to you, okay? So, Mike, today you demonstrated the fact that you have a 400-meter exclusion zone, that this is a walk-away safe reactor. The NRC that gave you that must have been convinced if they gave you such a small, exclusion zone, whatever. And so the two challenges for nuclear power to make a renaissance are cost and safety. It certainly seems like you guys have addressed the safety concern. What are you doing to get those reactors to be lower cost? Are you going to try to mass produce these in a factory? Are you going to try to project manage this so that the NRC never bothers you again and just lets you build them in quantity?
Yeah, so just to be clear, we have not completed the licensing process. We do have a safety case built, and we are engaged with the NRC to work through the licensing process. We're very confident that will work out as I described. With respect to the cost, there are several things that's not my area of expertise, but I will say that everything we're doing on the entire project is about design to cost. We're on a technical level, we're leveraging new technologies that are out there that will allow us to build multiple power plants, such as the boring technology that makes for instance, we're looking at the boring technology as being a way to save cost, and so we're building the plant to fit within that, specifically within that bore, with the idea that this is how we're going to build this thing. Because we're going to dig that hole in 3 years, in 4 years, this is where we're going to drop down in that hole. So really, with a sharp eye towards cost, and yes, modularization. I'm a big fan of the existing large reactors out there. They have struggled with cost. And one of the reasons is because it's been very difficult at that scale to achieve true modularization. Small modular reactors that are about a third of the size or less have a much greater opportunity to leverage building components and subcomponents and assemblies in factories, shipping them out to the site, bolting them together. So we are actively designing the plant to minimize things like the bespoke safety-related welding that has to take place on site. And yeah, everything we're doing is building the demonstration plant, but with an eye towards N+1, N+10, N+100 to really scale.
Yep, fantastic. We hope the utilities are hoping you're going to get there. Boy, they want that reactor.
Well, now I have a question for Mike. Because you said about the cost, safety, but the third component is what are you going to do with the spent material? So it's still a problem, right? So that is not maybe less quantity?
That is correct. I mean, it's a physical reality that there will be output from the process. Now, one of the advantages of using the fast reactor spectrum is that it allows us to extract significantly more energy out of the raw material. So we would anticipate, if an existing thermal water reactor extracts, let's say 10, 15% of the power from uranium, then sitting in that cask of spent fuel, there's still 80% of the power. By operating in the fast range, we would extract closer to 70, 80%, and then could even increase that through reprocessing, although that's a separate discussion I'm not ready to get into today. So we're not going to completely eliminate the spent fuel, but I can say that with the fast reactor technology that we and others are looking at now, we will have much less byproduct, and the byproduct that comes out will have much fewer harmful radionuclides. It actually gets burned up in the fuel process.
Okay, thank you. So my initial question was for Paul, and it's related to renewables. So we have gone through periods in our history where renewables were incentivized by the government, right? Solar and turbines, solar and wind turbines. But then you have the next administration deciding that it's not a priority anymore. Incentives are cut off. And so it makes the industry one that is not very attractive for investment or puts a lot of uncertainty in the investment. I somehow feel with this administration, big investment, but I still think we have this uncertainty of, will the next generation, next administration think differently, and then suddenly we have a much bigger problem than what you described.
Yeah, I have a couple of random answers to this. So in the past, there were supportive technologies for renewable, supportive incentives at the federal and the state level for renewable technologies, but the technologies themselves were very expensive. So it's not like those incentives, those government incentives, caused those technologies to take off immediately. But I think there's very little doubt that the reason solar and wind have become so incredibly economic right now is because there were investment opportunities because of past government regulations supporting them. I think if you talk to the states that are absolutely gung-ho to achieve net zero, and the current administration, federal administration, there's a lot of money going into R&D, and there are a lot of very specific policies that force the development and construction of advanced technologies that currently right now don't necessarily look economic. Battery storage is an excellent example. Offshore wind went from, we were Cape Wind, when it was being proposed to the state of Massachusetts back in the day, was something like 22 or 23 cents a kilowatt hour. And now the proposals that are coming into the Northeast states for wind power in the same area are coming in at 7, 8, 9 cents a kilowatt hour. So I think that the state policies absolutely have played an incredibly important role in pushing the technology to the point where it's economic and it becomes economic on its own. And you can start to walk away from the subsidization. And that's certainly the mindset of the policymakers that are pushing these technologies. One of the reasons I mentioned this isn't your normal public policy challenge is because in the past, when we have done pollution abatement regulations, it's always with an eye towards what technologies are available, best available control technologies. Whereas now, what's so different about climate change is we're passing requirements now in state legislation where we have absolutely no idea what's going to help us achieve what the policies state very explicitly. So not only have renewables really become an extremely important part of that, I think the states are banking on the fact that these regulations and incentives are in place will cause the technologies that will be needed in the 10 to 30 year time frame to emerge, like the ones that both Mike and TJ were talking about.
So this question is probably a combination for Paul and Mike. So unless my understanding is inaccurate, the current influx of offshore wind provides us with a lot of power that's needed, but again, unless I'm mistaken, the current infrastructure does not support accepting and distributing that power. And I'm wondering if you gentlemen have any insight behind that and solutions to it. And the part of this that goes to Mike is, are we going to face the same thing with the advent, or call it rise, of these fast nuclear plants? And then at the same time, we're faced with the increase on mass scale of electrification that the utilities are trying to put forth.
I can take a first cut here. I mean, you're highlighting what is absolutely the number one technical infrastructure challenge for decarbonization in the states that are pushing it. Right now, and I'll speak to offshore wind, and Mike can speak to nuclear, where, nuclear, you can locate it where the infrastructure exists. Offshore wind, not so much. You have to land it somewhere on shore. All of the proposals that have been submitted and accepted by states for offshore wind projects in the Northeast include in their price the cost of the transmission, meaning the transmission to get it from the wind farm to a location on the grid in PJM or New York or New England, but also what the grid operator says you need to invest so that that power can be moved freely throughout the region. So the responsibility of the developer is to pay for the transmission infrastructure to do it. Now, what the states are grappling with is that only amounts to 5,000, 8,000 megawatts of offshore wind that's currently being developed, and it can land and it can be used within those power grids. But the states want 3-4 times that amount. And everyone recognizes there's no way that we don't need some sort of massive transmission infrastructure build out to accommodate it. That can't be built into the price of that additional 10 or 20 gigawatts of offshore wind. So the states have, New Jersey has sort of went through an excellent process with PJM. Other states are doing the same thing right now to say, we can't have a separate line coming in from every single project. We need to figure out how the states need to develop an integrated transmission infrastructure without it being, done on a project by project basis to support the integration of all this. So it's a big issue. And not just with offshore wind, all the proposals for decarbonization involve build out, access to wind in the Midwest requires massive amounts of transmission investment. So I think there's a ton of, in the IRA, there's a ton of support for developing those types of transmission resources, but it's still, who knows whether or not it'll be enough. It's still a big issue.
Mike?
Sure, and so from the perspective of the natrium nuclear reactor, a sort of simplistic answer is, these can be scaled to size, but we've intentionally designed this first iteration of natrium reactor to approximate a medium-sized coal plant. And in fact, the natrium plant that we'll be building first in Kemmerer, Wyoming, will be taking the place of a retiring coal plant. And that's sort of the short-term, I don't want to say business model, but to address the problem about being able to, the idea is that as coal plants retire, the coal plant goes away, a natrium plant goes right there. There's existing transmission infrastructure right there. We don't have to do a lot of new siting. The construction is easy, and we won't have to worry about, say, the concerns that the wind does currently that you bring up. Additionally, the energy storage will ease some of the transmission. It will allow some flexing back and forth between renewables on the grid in that location. I hope that answers your question. Thank you.
All right, I think we have time for maybe one more question.
Real quick one for Mike. So Gen 4 reactors are walk-away safe, supposed to be. But I think one of your big hurdles that you have is public perception, which drives regulation, which also gets in the way and adds to the expense of making nuclear reactors. What are you guys doing to try to improve public perception for the new technologies that you have available?
That's a great question. It's a bit out of my lane, but I will say, we're actively participating in organizations like the NEI, Nuclear Energy Institute, where we're trying to get the word out through forums like this. Also, the Nuclear Regulatory Commission is not blind to this issue of climate change and the need to decarbonize the grid. And the Nuclear Regulatory Commission is our partner. They're not our enemy, but they do fully, I believe that they recognize the perception and the truth that any regulation that is burdensome in nature and does not add value really needs to be cleaved away so that we can focus on the actual safety case. And they've come to the table, and they have passed new, as I was mentioning, our safety case will be built largely on probabilistic risk models rather than the old school deterministic models, which tended to lend to over-engineering and over-regulation. So I think there's some progress in the area of regulation that's helping that. As far as public perception, we just have to continue to operate without, with zero accidents and try to, it's an education exercise more than anything else, I guess.
A TikTok video. There you go.
You write that down.
I could add one point on this. So I teach a course, introductory energy course at Georgetown, and when I started about 5 years ago, all the students were super excited about solar and wind. So all the papers that they wrote were about solar and wind. In the last 2 years, I have had a surge in papers written about nuclear, SMRs in particular, and I think it just speaks to the fact that they are seeking sort of this next, what is the next big thing in a lot of cases, and they're willing to kind of, give nuclear a chance. And that's important, I think, in that for that generation as well, just knowing that, there's so much focus on climate. So I think it's a useful anecdote that I've kind of told many people, and they're in some cases surprised, actually. So.
Great. I'd like to thank our speakers for coming and for our audience.